Okay, thank you. Yeah, so I'm going to talk about several things related to axions. This is work that's been done with many collaborators. I'm not going to read all the names. Several of them are here in this room. Here's a brief outline. I think since I submitted the abstract for this, I decided to actually add a bit about some work in progress about dark matter and dark energy, which is maybe a bit closer to some of the themes we've been hearing about over the last couple of days. So let me start with a quick introduction. Probably most of you have heard about axions before, but just in case. There's something called the strong CP problem, which was the origin of the original motivation of axions. Theories like QCD admit a term that violates time reversal symmetry or CP symmetry, which is this kind of anti-symmetric contraction of gluon field strengths. And it has some very interesting properties. It's a topological term. This integral of trace G wedge G over a closed manifold is a topological invariant of the gauge field configuration. It's locally a derivative of something called a Chern-Simons current. And so the effects are very subtle because it's locally a derivative of something. It has no effect on local equations of motion, but it has interesting physics nonetheless. And in theories with fermions, you can rephase a charged fermion, and due to the chiral anomaly, that can remove this term, but then it pops back up somewhere else in the phase of the mass term. And so physics only depends on a combination we call theta bar, which is theta minus the phase of the determinant of the quark mass matrix. And it's been known for more than 40 years that there's a simple physical observable that can actually be measured that is related to this term in QCD, which is the neutron electric dipole moment. So electric dipole moments violate time reversal symmetry because they look like electric fields dotted into spins. If you reverse the direction of time, spins go the other way, but electric fields don't. And so you can do clean measurements because time reversal is a good symmetry of most of the physics of the world around us. And if you see things that violate it, they tend to sort of jump out of the data. So people are very good at measuring them. Cruther, DeVecchia, Veneziano, and Witten estimated in 1979 that the size of the neutron EDM is proportional to this T-violating parameter. It's roughly the size of the neutron suppressed by the up quark mass over lambda QCD because of this chiral anomaly effect. The physics of theta has to disappear if there's a massless quark, so it has masses of quarks in the numerator. And it's something like 10 to the minus 16 centimeters times this parameter theta bar. But experimental bounds tell us the neutron EDM is smaller than something like 10 to the minus 26 centimeters. And that implies this parameter is smaller than 10 to the minus 10. And that's strange because we already know that time reversal or CP is not a symmetry of nature. So why is this parameter that we're allowed to write down such a tiny number? And there was an answer that was proposed to this back in the 1970s by Peche, Quinn, Weinberg, and Wilczek, which is that if you promote this constant parameter to a field, make it theta of x instead of just some number theta, and give this field a kinetic term, now it's able to respond to strong dynamics, and you can compute that the potential energy is minimized when this parameter is 0, so when you turn off the CP violation. And in particular, you can estimate that the mass of the corresponding particle, that's the excitation of this field around the minimum, which we call the axion, is roughly set by things involving QCD divided by this number f that appeared in front of the kinetic term. If f is 10 to the 12, this is something like at the micro EV scale. And so it's a very light particle, but all of its interactions are suppressed by 1 over f. And so if f is a large number like this, we can have not seen it in experiments yet because it interacts very weakly with everything we observe. So that was the original axion idea. It turns out this is not a very satisfying solution to the strong CP problem because what the work of these people showed was that this solves the strong CP problem if you write down precisely this Lagrangian. But you can ask, why should I not write all kinds of other things involving this field theta of x? Usually if I write down a scalar field, I'm allowed to write a potential, I'm allowed to add all kinds of things. And if I do that, even if I write other terms in the potential, like this V other that I just sort of put in by hand, that are small compared to the QCD generated potential, if their minimum is in a different place than the minimum of the QCD generated part, then when you add them together, you can shift the minimum. And even something much smaller than the QCD generated potential can easily give you an answer that's way bigger than 10 to the minus 10. Yeah.
Are there standard model contributions to the other? Because
yes. because the CKM phase violates CP, there are other contributions. Those contributions are actually quite small, so we don't really need to worry about them. I'm forgetting that there's a prediction for if you only had a CKM contribution to the neutron EDM, what would it be? And it's orders of magnitude below the current experiments. Sorry, what? The effective theta that you generate. Yeah, okay, thanks. Yeah, so it's way below current constraints. Okay, but in principle, why should I write anything that's smaller than VQCD? I could just write something, some Planck scale potential if I don't have some other reason not to. Okay, so we really need a better model of this, and this is what people call the quality problem. You can be more quantitative about it. So a lot of the traditional axion models assume it's the phase of a complex scalar field. There's some approximate U1 Peccei-Quinn symmetry that acts on this that's spontaneously broken, and the axion is a Goldstone boson. And I can just write down operators like phi to the n, why not? And calculate the effective potential it generates. And even if this power of n is very big, and I suppress it by a high power of the Planck scale, because I'm fighting against the QCD scale, which is exponentially small, and this additional 10 to the minus 10, this can very easily just totally ruin the strong CP problem unless you can forbid all of these operators up to some very, very big number. You can do it. So you can invoke something like a discrete gauge symmetry that rotates the phase of phi. If I rotate phi by e to the 2 pi I over p, I can forbid every operator up to phi to the p. So if I invoke such a symmetry with p equals 14, I can claim to have solved the strong CP problem. But it's not a very pretty thing. You're sort of putting in this awkward new symmetry by hand. In some cases, this thing that you do also tends to mess up the cosmology. So we can ask, is the axion really a good solution to this problem or not? Let me come back to that in a moment when I tell you about what I think is the actually good solution. First, I want to have kind of a disclaimer. I'm talking about the QCD axion. That was the original one. But there are also axion-like fields. And so if somebody uses the word axion, they might not mean something that solves the strong CP problem. They might just mean some other periodic scalar field. We don't tend to call things like the pion an axion. So if I wanted to say, what is it that people mean when they say axion? Usually it's a light scalar field where the potential is coming from some sort of instanton effect and some sort of couplings of the theta FF tilde type to gauge fields are important. And these general axions may play a role in things like dark matter or dark energy or inflation beyond just the strong CP problem. All of these have some version of the quality problem in the sense that we don't have to explain the neutron EDM for all of these if they're not coupling to gluons, but we do have to explain why they are light fields. Why don't we just write down a big potential? One other general thing I want to say before I get to more specifics is to tell you about something called the Witten effect. This was another 1979 paper of Witten, the same year he calculated the neutron EDM. He noticed that the theta term for QED has an interesting physical effect, which is that in the presence of a theta term for QED, if you can find a magnetic monopole, the magnetic monopole will acquire a fractional electric charge. So there are two charges in the theory, a magnetic charge QM and an electric charge QE. And in the presence of a theta term, you can show that QM still is an integer like you would have thought all along, but QE is now an integer plus QM times theta over 2 pi. And so if you have a monopole where QM is not 0, it picks up a new piece of its electric charge proportional to theta. In particular, that means that if there's an axion-like field, if theta is now a dynamical variable, as it fluctuates, if you can find a monopole, the electric charge of the monopole will fluctuate too. And so the only way to consistently have an axion in a theory with the monopole is that the monopole has this extra degree of freedom that lets it acquire electric charge. So we call this a dion mode associated with the monopole. And in the presence of this mode, the monopole mass will depend on theta. So as you turn on theta, you give it electric charge, it acquires a new piece of its Coulomb field, and there's a new contribution to its energy or its mass. And you get some formula like this, and this will play a role in what I'm going to talk about in a moment. There's some integer that labels this combination of electric and magnetic charges, and for these dions, if theta goes to theta plus 2 pi, physics is periodic, but the individual modes are not. So what happens is that this integer n has to shift to n minus 1 in order for this combination to stay the same when you shift theta to theta plus 2 pi. We call this kind of rearrangement monodromy. So there's a bunch of different states. When theta goes around its circle from 0 to 2 pi, the states sort of shuffle along and each one becomes the next one. So the whole set is the same, but they've rearranged. Okay, so that's a very quick overview of a lot of interesting things about axion physics. Now I want to tell you about the cosmology chunk of my talk. This is work that I'm doing right now with my former student, Hengame Bagarian, who's now a postdoc at Chicago, along with Lian-Tao Wang at Chicago, and Huangyu Xiao, who's a postdoc at BU and Harvard. We're thinking about interactions of dark matter and dark energy. And we're thinking about something where there's a fair number of recent papers that have been playing with things like this, especially in light of the DESI data that we've been hearing about over the last couple of days. One way you might try to have some kind of interaction between dark matter and dark energy is to say there's a light scalar phi. It's evolving in a potential V of phi that gives rise to dark energy. There's some massive dark matter field chi. And let's suppose the mass of chi depends on the value of phi. So that as the scalar field is evolving in its potential, the dark matter mass is changing with time in some correlated way. This is one interesting way that you might try to get a non-trivial equation of state that's evolving with time as you're sort of rearranging energy between dark matter and dark energy. But in order to do this, if you want to think of phi as dark energy, it needs to be very light, so around Hubble today or lighter. And chi needs to be heavy because we want to think of it as dark matter. We want it to be oscillating in its potential. If it's a scalar or if it's a fermion, it needs to be massive enough to fit to let galaxies form without Pauli degeneracy pressure ruining things. And so there's a naturalness question, just as a low energy effective field theorist. When I see two fields that couple to each other and have very different masses, I start to worry that loops of the heavy field are going to raise the mass of the light field. And the concrete way that can happen is the Coleman-Weinberg potential. So you integrate out loops of chi, you get some effective potential for phi. It involves the mass squared as a function of phi multiplied by some cutoff squared, plus the mass to the fourth times a log, plus various other kinds of things. And so we just stared at this potential and thought about what might we like a model like this to do. One thing you might like a model like this to do is to have an interesting interaction between dark matter and dark energy. And what I mean by that is that if the mass of chi is phi dependent, phi has some effect on chi by changing its mass. But conversely, chi has an effect on phi because if you have a population of chi particles in the universe, there's some density of chi, and then there's a term that multiplies m of phi by that density, so that acts like an effective potential for phi. Okay. So there's an induced effective potential for phi that looks like the phi-dependent mass of chi multiplied by the number density of chi particles that are around in the universe. And so what we ask is that this induced potential for phi dominates over the kind of bare potential, the part that didn't depend on chi. We're demanding that just to say, if that doesn't happen, then this interaction is not all that interesting from the viewpoint of the dark energy dynamics. But if it does, then something interesting happens. Now, if that happens, this induced potential is bigger than V of phi. But we also want V of phi to be big compared to the Coleman-Weinberg potential we calculated here, or our effective field theory isn't under control. So you put those together, this induced thing is bigger than the Coleman-Weinberg potential. They both involved this m of phi in some way. And so you just put the pieces together, and what you learn is, well, first, either V of phi was just fine-tuned, so it wasn't actually bigger than the loop correction, and we don't have a good effective field theory. That could happen, but it's not very nice, not a very good theory. Or maybe the Coleman-Weinberg calculation was wrong. There's some natural mechanism that makes it small. That would be an interesting and good thing. Or you just put these inequalities together and you learn the number density of chi has to be a lot bigger than its mass cubed. And whenever that happens, that means you're in what we call the wave dark matter regime. So dark matter isn't really behaving like particles because the interparticle separation is small compared to the de Broglie wavelength of the particle. And you have high occupation numbers. In particular, you end up in this regime where chi is lighter than an EV. It has to be a boson. And your model building is sort of very restricted. I saw a hand go up back here.
Sorry, do you want that domination? Do you want that only happen in the dark matter dominated era?
Yeah, so I want it to happen at some point in the matter dominated era. Yeah,
And the dark energy dominated era, you want to be
it isn't necessarily true today, right? So there could be a transition between this dominating like around the time of matter radiation equality, and today when it turns off and we're just in the bare V of phi. Yeah. So as the dark matter redshifts, there's some non-trivial evolution of this thing, and it becomes less and less important over time. Yeah. Thank you for.
So these properties are very similar to the model I guess George has talked about. But for us, mass of chi is a tower starting around milli electron volts.
Uh-huh.
But the rest of what you said sounded very similar.
Okay, I wasn't at George's talk because I had to leave to pick up my kid from daycare yesterday, so I apologize.
Look at the evolving dark sector paper.
Okay,
So the
yeah.
model has both the mass dependent phi, chi dependent phi, and it satisfied. The motivation was very different, of course, from what you're doing. But parameters were right.
Okay, I'll compare notes on that. Yeah, thanks. So there's this wave dark matter option. If you try to do this with just two fields, we found it's not easy to build a full model. And we thought more about this option. Maybe the Coleman-Weinberg calculation is just wrong for some reason. Maybe there's some cancellation. And I know of at least two ways that can happen. And interestingly, both of the ways that I know involve some form of what's called axion monodromy, this thing where as the axion goes from 0 to 2 pi, some states rearrange themselves. One of those ways appeared in a paper last year by Justin Khoury, Mengxiang Lin, and Mark Trodden, where they're building on a field theory mechanism that Anson Hook proposed several years back. Their idea is dark energy is a light axion. Dark matter is in the form of dark baryon. So there's some dark QCD sector and it has its own proton-like states. And those are the dark matter. But crucially, to make the Coleman-Weinberg potential not give you the right answer, they assume that there are a bunch of different copies of dark QCD and there's some ZN symmetry that permutes them. So each one sort of becomes the next one in the chain. And their relative theta angles are staggered. So the first one has angle theta, the next one has angle theta plus 2 pi over n, the next one has angle theta plus 4 pi over n, and so on. When you do that, you do the Coleman-Weinberg calculation, you get a bunch of different potentials, but they have different relative phases and they destructively interfere with each other. And it turns out that the potential you get is exponentially small in some parameter. So that's one way of doing it. What Hengame and Liantao and Huang Yu and I are thinking about is a different way of canceling the potential, which builds on some other work that I did with Gigi Fan, Katie Fraser, and John Stout a few years back, where we showed that if you have magnetic monopoles that have this dion mode I was mentioning, so there's an electric charge the monopoles can acquire, and when you shift theta to theta plus 2 pi, they rearrange themselves. There's again, a kind of conspiracy where the loop corrections from each of these states roughly cancel with each other. And what you're left with is an exponentially suppressed thing that depends on kind of the ratio of the monopole mass and some measure of how split the different electrically charged states are, which for like an Atuf-Polyakov monopole, that would be like the W mass. But in general, there's some number like that that appears inside an exponential. So yeah.
Is there mass of the monopole is into infinity, then there's no vacuum energy. Is there an understanding for like symmetry-based understanding why there's not more than one per?
Oh, when you send the mass of the monopole to infinity? Yeah,
Like what's the
right. So in order to generate a potential, let me think. In this context, sorry, I don't want to spend too much time thinking this through on the spot. I think the statement that is true is that you need to break the magnetic one-form symmetry, or there is some sort of non-invertible symmetry protecting the axion. I think that's the explanation of why. Yeah, because the shift symmetry of the axion becomes a good continuous symmetry in that limit, and so the potential is independent of theta. Yeah. Of course, there is some divergent overall constant vacuum energy here, but I'm just talking about the theta dependent part is this. Yeah. Okay. So the upshot of this is that we were sort of thinking about general arguments about dark matter and dark energy, and we're sort of led to two interesting directions. We're sort of pursuing this one, and maybe this is also an interesting thing to think about. As Kamran said, this is maybe related to some of the things in George's talk. But interestingly, both options are pointing toward light bosons, right? Wave dark matter is light bosonic states. And here, these natural mechanisms we know about involve light axion states. And this is super preliminary. We're still in the process of convincing ourselves we're working with a viable benchmark point that isn't ruled out by something. But just to show you that in this kind of model, it seems that we are able to get interesting evolution of W of Z kind of in the redshift bins that, so this W effective, the dashed line, is really the thing that you should be comparing to the data. And it seems like this kind of model is capable of having this evolve in an interesting way. Okay, so that was the first part of my talk. Yeah, okay, question.
In this model, the mass of the dark matter particles, are they going up in the dark matter dominated area, or are they going?
They're going down but they're not changing a lot because it's mostly the monopole mass, and then there's these little ionic corrections on top, and it's the little corrections on top that are changing.
Our model went down 3% during the matter dominated era and went up 1% during dark energy. What is it in this case?
I don't think I know the precise number off the top of my head, and we're also still kind of in the process of getting the details right. But I think probably percent level is similar. Yeah, I'd have to double check.
You're fitting this to the MCM, like MCM dizzy runs?
No, I think this is just fitting to these points in error bars. This is not a really detailed cosmological fit at this stage. Yeah.
So does the equation state of dark matter change by a lot?
The dark matter is not changing a lot, but the dark energy is, because its effective mass starts out big and sort of redshifts with the dark matter. So at first it's redshifting similarly to dark matter, and then it's kind of transitioning to dark energy like. Okay, so all of that is just to try to sell you on the idea that axions are interesting not only for the strong CP problem, but also maybe doing non-trivial things in cosmology that fit the kind of theme that we've had in the last couple of days. Yeah.
But just going back to your last sentence, so during the matter domination era, the phi field is also oscillating like matter, but like later on, it's starting to act like that.
No, it's not oscillating. It's sort of evolving down the slope of its potential, but the size of the potential is changing with time as this n chi dilutes away.
But mass always less than
The mass is always less than Hubble.
It's true.
It's sort of order Hubble. It's kind of like decaying in a way that's sort of tracking the expansion of the universe. Yeah. Yeah.
Sorry, maybe I missed it. Sorry if that's okay. But in the context of axion, how would you produce these like chi particles as dark matter? So are you assuming
The phi are not dark matter. The chi are the dark matter.
Yeah. Phi, how do you?
So for us, the dark matter are the monopoles. And so that's a story. So at the moment, it's looking like the most viable version of this is to produce them through Friesen in the early universe. But that's sort of one of the things we're actively thinking about, is different ways that we might get the dark matter abundance right. Which is one of the reasons I don't want to commit to anything more than very preliminary here. We're trying to check that all of that hangs together. Yeah.
How heavy are these dark? How heavy are these dark monopoles?
Oh, they're very heavy. I'm forgetting 10 to the 10 GeV or something like that. Huang Yu, do you remember the?
Could be all the way from 10 to the 5 to 10 to the 10 GeV. You know, that mechanism produced.
So maybe once we've decided which mechanism we're going with for sure, I can give you a more precise number. But they're very heavy. Okay, so that was part of my talk. Now I'm going to sort of change direction and circle back to axions in extra dimensions and axions in string theory, and kind of how these things that I've tried to tell you are phenomenologically interesting actually fall out of fundamental theories. So I told you about the quality problem, and the quality problem is the problem that you don't want to have new contributions to the potential, right? So it's okay to have derivative interactions, but you don't want to have anything that has theta without a derivative, because that could lead to a potential. And so you can ask, well, what is a way to get things that have derivatives but not the field itself? And we know that happens very easily with gauge theories, right? In gauge theories, we can't write down any random thing involving a mu because it's not gauge invariant. But we can write down anything we want involving f mu nu because it's gauge invariant when we take the derivative. So that suggests that gauge theories are good ways to get things that look like they solve the quality problem, in the sense that they involve derivative interactions, but the non-derivative interactions are very controlled. And this idea is realized in the context of extra dimensional models, where the axion comes from a higher dimensional gauge theory. These actually go back to fairly early days. Witten in 1984 And one of the very early papers on superstring theory observed that you have some sort of generalized gauge fields in string theory that can play the role of axions. It took much longer for this idea to sort of filter down to the phenomenological axion literature, but it's there very early on in the string theory literature. And if I have a gauge theory and I want to know where can I see A without a derivative, the answer is, well, charged particles have covariant derivatives that involve A. And Chern-Simons terms, so things like A times field strengths. These are Chern-Simons terms are things that are not actually gauge invariant terms in the action, but where e to the I action is gauge invariant. So they're kind of subtle, but they're things that we are allowed to write. And if I start with a gauge theory in higher dimensions and I reduce to 4 dimensions, I can realize an axion-like mode by integrating gauge fields around an extra dimension. So the simplest case is start with a 5D theory with a circle, integrate A5 around the circle, you get an effective axion. If my higher dimensional theory had a Chern-Simons term and I reduce to 4D, that becomes exactly the axion coupling to gauge fields that we want to solve the strong CP problem. And the nice thing about these theories is that the quality problem can only be spoiled by these very special things. Either other Chern-Simons terms, so like maybe there's a different gauge theory that couples to theta and generates a potential, or by charged things, things that carry a charge under A. But if those are massive, then the effective potential they generate is always exponentially small. So they have to propagate around the extra dimension in order to produce an interesting effect, because within the higher dimensional theory, I'm just not allowed to write a potential for A. So any potential that you generate for theta in the lower dimensional theory somehow has to know about the whole extra dimension. And you can show that these things go like e to the minus mass of the field times the size of the extra dimension. So that means extra dimensional axions are relatively safe. It's not that they automatically solve the strong CP problem. You have to check these different contributions in your particular theory, but there's a finite list of things to worry about. And the things that you worry about are naturally exponentially small. And so you have a fighting chance of solving the problem. In string theory, this happens in a generalized way. Instead of having a gauge field A mu, we might have a p-form gauge field that has many indices. It's some anti-symmetric tensor. And instead of integrating around a circle, we integrate over some p-dimensional cycle inside the extra dimensions. But other than that, the story is very much the same. You can have Chern-Simons terms that lead to the kind of coupling you want to solve strong CP. You can have charged objects. They're not particles anymore. They're strings or membranes or higher dimensional things. But the upshot is that the theory can solve the problem. And in kind of modern language, we say that the axion quality is protected by a global symmetry, which is the approximate electric p-form symmetry of the higher dimensional gauge theory. Now, these extra dimensional axions are very different from the classic 4D theories. In particular, in the 4D theories, you have some sort of phase transition where a PQ symmetry is broken. In the extra dimensional theories, you don't. There is not some temperature at which you had a U1 symmetry and it breaks and you get some emergent Goldstone boson. You just sort of had the gauge field all along. It has a zero mode all along. And so if you're familiar with the discussion of axion cosmology in terms of pre versus post-inflation, these models are always pre-inflation axions in cosmology. We expect the energy scale associated with the axion is some sort of UV scale, and I'll try to be more precise about that as I go along. Okay, so that was sort of general field theory comments about extra dimensions. Now let me say some things about string theory. There is a large landscape of consistent quantum gravity theories containing gauge fields. We know many examples of string compactifications that have gauge fields. And a thing that you often hear, especially from people who think about string phenomenology, is that axions are ubiquitous in this setting. You often even hear that we should expect many axions to exist, a string axiverse where there are dozens or hundreds of axions in the world around us. Maybe one of them solves the strong CP problem and the others, maybe some of them serve as dark energy or play other roles. These come from starting with some complicated higher dimensional geometry and integrating the different higher dimensional gauge fields over different dimensional cycles. And if your topology is complicated enough, a single higher dimensional gauge field can give you many axions because there are many different cycles you can integrate it over. Now, a thing that I have wanted to know for a long time is how seriously should I take these words people say about these being ubiquitous? Is it really a prediction of string theory that an axion should exist in our universe? Or is it sort of a looking under the lamppost thing that we build some particular constructions and we find them there and we just don't know enough to ask the question in general? And so what I want to talk about now is sort of my thinking on why I think that there might actually be a good general reason why string theory predicts an axion in our universe. But I want to emphasize that it is not that anytime you find any gauge field in quantum gravity, it must couple to an axion. That is just a false statement. There are counterexamples. And so any careful statement needs to somehow deal with all the different examples.
False statement. Do you mean
Yeah.
massive axion or light axion?
I mean light axions. Yeah, yeah,
Because
yeah.
massive axions
Oh,
are very hard to.
It's hard to know what it even means if we're talking about arbitrarily heavy states.
Because in
Yeah,
Swampland,
sure.
they always are massive axions.
Yeah, sure.
At least for any equation.
Yeah. I really mean light axions that only get potentials from some sort of instanton effect as opposed to like big tree level potentials. Yeah. So here's some reasoning that suggests to me that there might be something interesting going on here. I'm going to take a detour to more than 4 space-time dimensions. So I know the workshop has our universe in the name. I'm going to come back to our universe, but for now, let's suppose we lived in a world with more than 4 space-time dimensions. In such a if we have a gauge theory, an SUN gauge theory in more than 4 dimensions, the instanton number density, 1/8 pi squared trace f wedge f, is the generator of some kind of global symmetry. It's a conserved current. You can just take its derivative and do a little bit of algebra, and you end up seeing that its derivative is equal to 0 if you assume what's called the non-abelian Bianchi identity, that the covariant derivative of f is 0. And we say that the symmetry generates what's called a d-5 form global symmetry, instanton number symmetry. Now, global symmetries make sense when this is a p-form global symmetry where p is greater than or equal to 0. If I plug in d equals 4, this is a -1 form symmetry, and that's a kind of a degenerate thing that you have to be careful about what it means. But at least if I'm in more than 4 dimensions, this is just an honest global symmetry of the type that we understand very well. This is for SUN, but this generalizes to any gauge group. And with several other people, Ben, Jake, Miguel, Tom, and Irene, a few years back, we were thinking about this kind of symmetry, these symmetries that are generated by field strengths in gauge theory, and thinking about the belief that quantum gravity does not allow global symmetries. I should say these are generalized U1 symmetries. These are kind of the place where we're on the strongest possible footing for saying these don't exist in quantum gravity. There are many arguments. There are black hole arguments. There are holography arguments. And so something is wrong with the belief that gauge theories have these symmetries. These gauge theories can exist inside string compactifications, but string theory is a quantum gravity theory and it shouldn't have these global symmetries. How do we resolve this tension? And there are basically 2 options. If you have an unwanted symmetry, it had better either be gauged or broken. If we gauge the symmetry, the simplest way to gauge the symmetry is to just add a gauge field coupled to the current. So I add some new gauge field C that has a C wedge trace F wedge F coupling. That's a Chern-Simons coupling. That's something we're allowed to do in field theory, and it's something that also shows up very often in string compactifications. The other option is to say, well, something was wrong with this argument that this was asymmetry, that the current is conserved. But what could go wrong? This was a very general argument. It only depended on the Bianchi identity. But the Bianchi identity can be broken. It can be broken in theories that have magnetic monopoles. And so that's one way that you can break the symmetry, is to say magnetic monopoles exist, break the Bianchi identity. This thing is not symmetry anymore. Okay, back to d equals 4. I would like to believe that in d equals 4, something very much like what I just told you remains true. The arguments become harder to make super convincing and rigorous, but there are a lot of analogies. There's also another old idea, which is that in quantum gravity, there shouldn't be free parameters. There shouldn't be continuous free parameters. Any parameter of the theory should either be the bev of a scalar field or should sort of be frozen to some discrete set of values. So our 2 options then, we had the gauging option. The gauging option was giving a Chern-Simons coupling of something to instanton number density. And in this context, the analog of that is to add an axion theta and couple it trace F wedge F. Question? Yeah.
Do you need more than one single factor to have magnetic monopoles and axions at the same time? Owing to the fact that one gauges the symmetry and the other breaks?
No, I think I'm going to come back to that in a slide or 2. So yeah. Okay, so we can gauge the symmetry. by adding something like an axion. A precise sense in which you can think of this as gauging, even though this isn't an ordinary symmetry, is that the instanton number is the integral of this current. The equation of motion in the axion theory sets that equal to a derivative of the axion current, and the integral of a total derivative is 0. So we have removed the net charge, which is what gauge theories do. Right? It's like a Gauss law constraint that tells you in a closed space you can't have a net charge. Except here it's space-time instead of space. That's the way in which this d=4 case is kind of funny. Option 2, violate the Bianchi identity. Magnetic monopoles do this. And in this context, we expect that when this is the thing that's happening, theta is somehow frozen to some discrete set of values. There are examples that do this. I think I might have it on a slide or two, but Cumran and Sergio Chicotti wrote a paper with a nice example of this several years back. So here's what I'm proposing, that in quantum gravity, either option 1, theta is a dynamical field, which is a light axion in the low energy theory. There's kind of an option 1 prime, which is there's sort of a modified thing you can think of as gauging where you have chiral fermions and a Green-Schwarz mechanism. Let me not linger on that because it would take me too long to explain to the people who aren't familiar. But basically, both of these options you can think of as different ways of gauging instanton number, and both of them actually happen in known string theory examples. Option 2 is that for some reason theta is frozen to discrete values. Yeah, and here's the Chicotti-Vafa reference that I was just mentioning. Now, a pattern that seems to hold up in examples that I understand is that gauge theories that contain light, minimally electrically charged fermions always have light axions. So they're taking option 1. Really, I mean, they're taking 1 or 1 prime. But again, I'm going to sort of sweep subtleties under the rug for limits of time. And so here's what I want to suggest. This folklore that there are no free parameters in quantum gravity, I want to say in this context where the parameter is a theta term. Yeah.
The condition I missed, can I go back to?
Yeah, when there's a light, minimally electrically charged fermion.
So in the example we were studying with Chicotti, if I remember, it was n equal to pure supergravity.
Yeah, so everything charged was very heavy. So your U1 was coming from C4 reduced on a 3 cycle in type 2b, and the charge states are D3 branes wrapped on the 3 cycles, so they're very heavy. So the examples I know have that flavor, where the things that carry electric charge are very heavy objects. Okay, so what I want to propose is that if the gauge theory can be consistently coupled to a background axion, then it will be consistently coupled to a background axion. Again, with some fine print that I'm sweeping under the rug. And this resembles the fact that there are no global symmetries, right? So if you have a global symmetry that you could couple to a background gauge field, then in quantum gravity, there must be a gauge field that couples to it. Now, every gauge theory has a theta term, so the question is, when am I not allowed to turn it into a background field that I can couple to? And I've told you that monopoles seem to be a thing that can do this, but now circling back to the question, sometimes they don't. Sometimes the monopole doesn't break the symmetry, or more precisely, sometimes the monopole breaks the instanton number current that I wrote down, but there is an improved current where I add another term to it that becomes conserved. And that happens when the monopole is a Dion mode. So physically, this is about the Witten effect. If I have an axion and the axion fluctuates, the Witten effect tells me the monopole had better acquire an electric charge. Some monopoles are equipped to do that. They come with a degree of freedom that can turn on and give them an electric charge. And then it's okay to couple them to an axion. Some monopoles don't have that. A familiar example is the Kaluza-Klein monopole. If I compactify a gravity theory on a circle, there's no Dion mode, and so you can't couple it to an axion. There's no way for it to be consistent because it doesn't have the right degree of freedom to acquire electric charge. And you can check Kaluza-Klein monopoles that come out of consistent theories like string theory, and they do not have axion couplings. So the cases where we find no axion are the ones where you have a monopole, but it just doesn't have a way to acquire an electric charge, and therefore there's no way to couple it to an axion. So what I'm suggesting is that if it does have a way to acquire an electric charge, then it must couple to an axion. I don't have a proof of it, but it's consistent with all the examples that I'm aware of. And the reason why light fermions come into play here is there's this great fact about monopoles that if you solve for the modes of a fermion around a monopole, they act like bosons. That's because there's angular momentum stored in the electric and magnetic fields. And so a minimally charged fermion has an S-wave mode, which means in a monopole background, you can just take some sort of spherical shell of fermion that carries electric charge and just drop it onto the monopole core. And there's no obstruction to that. There's no angular momentum barrier. And so all the theories with minimally charged fermions kind of automatically have this Dion mode. because there is this way to deposit charge in the core. There's no obstruction to it. And I'm suggesting that that means that there's also no obstruction to axion couplings, and so these theories actually need to have an axion. And the standard model is of this type. Okay. So none of this was a rigorous argument. It's all sort of suggestive, but it's arguments that sort of look closely analogous to things where we have more weight behind them, like no global symmetries in higher dimensional theories. So, so I'm suggesting to you that axions are not totally universal in quantum gravity, but for standard model-like theories, I think maybe they are.
So
Yeah.
I vaguely remember something about breaking B minus L symmetry. Is there a model with monopoles? Does this happen? That if I have a magnetic monopole, there's this Kalin-Rubikov effect?
Yeah, so the Kalin-Rubikov effect is closely related to the physics of these S-wave modes. And sometimes that does break some global symmetries. It depends on the details. Well, it depends on the details. I think in SU5, it only breaks B plus L and not B minus L.
I'm just asking because there's B minus L in the book.
Yeah. Question?
So you're saying that in theories with light fermions, you automatically get these axion couplings, but did I miss it? Are the axions light here, or can they still?
Yeah, so I'm suggesting that whenever this is true, the axions actually have to be light and only get a mass from instanton effects.
Have you explained that?
Probably not very well, and I'm not going to. We can talk more about it sometime, but given my time here, I'm sort of giving the broad brush version of the argument and omitting a lot of discussion. Yeah.
Sorry. Why is it important for you that this is a fermion if I have a minimally charged boson, for example?
Oh, because those don't actually let you deposit charge on the core because they're because the bosons in the monopole background behave like fermions. And so the boson always has an angular momentum barrier. Yeah. Okay. Okay, so I don't know if that was convincing or not, but that's at least sort of the current state of my thinking is that I now kind of believe that it's probably true, that it's not just a lamppost accident that when people find standard model-like things in string theory, they find axions. I think there's some underlying general structure that's kind of forcing that to be the case, which at least makes me more excited about the prospects for actually finding axions in the world around us. Which brings me to the last part of my talk. Now I want to ask, suppose we go the other way.
Just one question.
Yeah.
Could that be related to the statement that if the fermions were massless, then the axion can be shifted away?
Yeah, I mean, so in particular, there are examples where instead of an axion, you really do have massless fermions. And so like some examples where there's a Green-Schwarz mechanism, I would say the instanton number is actually gauged by the fermion instead of the axion. It's almost like the phase of the fermion becomes sort of the effective axion.
Right. So would that fact be related to if you start with a theory which is not light but massless and then break it to get light, then you will have automatic data.
Yeah, if you could start in such a limit and perturb away from it, I think that's probably true. But I don't know that every example like this can sort of start with that and perturb away from it. But I think right. I think there's I think there's probably something interesting to say along those lines. Okay, so the last thing I want to talk about today is suppose that we do find an axion. Right? Suppose that there is a discovery of axion dark matter, and what do we learn? If it's a QCD axion, you would learn two things from a discovery. You would learn the mass. And at least for most of the experiments that are looking for it, you would learn the coupling to photons. Now, the mass of the QCD axion is predicted in terms of its decay constant F. And the coupling to photons is a little bit more model dependent, but it's basically an order 1 number times alpha divided by 8 pi F or something like that. So roughly speaking, the kind of UV information you get from a low energy experiment that sees axions is this 1 number F. Some dimensionful scale, which on the low end from astrophysical bounds can't be too much smaller than 10 to the 9 GeV. And on the high end from sort of theory bias is probably not much bigger than 10 to the 16 GeV. And this range of scales is interesting because They're all well below the Planck scale. Again, I'm putting in a little bit of theory bias when I tell you I think the upper end is below the Planck scale. They're also all way above the TeV scale. So this would be one of very few signposts we have about some scale in physics that is far above what we can access in terrestrial experiments, but far below the Planck scale. So what would we learn about fundamental physics from this? And for a conventional 4D axion, physics is four-dimensional at the scale f, right? Some symmetry breaking phase transition happens at the scale f. And for the extra-dimensional axion, it's actually kind of the other way around. And I find the extra-dimensional axions more plausible. They're better solutions to the quality problem, as I was trying to sketch. They also tend to be the kind of thing that falls more naturally out of string theory. So here's a warm-up. In the 5D case, you can say, how do I get f? I start with a kinetic term for my U1 gauge field in 5D, and I dimensionally reduce. And when I do it, I learn that f squared looks like 1 over gauge coupling squared times r, where r is the radius of the extra dimension. If I want to have any control over what I'm doing here, I can't have E5 be too big. In particular, I want it to be small relative to r, in the sense that 1 over E5 squared is bigger than 1 over r. And then if I plug that into this, I learn that f is bigger than 1 over r. 1 over r is the kk scale. That's where you start seeing the extra dimension appear. And so if an experiment tells you f, and you want to interpret it as a 5D axion, you learn that 4D physics breaks down at or below that number f. That's for a 5D model. 5D is simple because we just have one extra dimension. It only has one parameter that is its size. More general things are hard to talk about because once you go to more than one extra dimension, you have many different manifolds. They have many different shapes. They have multiple parameters characterizing them. It's harder to be super quantitative. But I want to propose something that I think we have some interesting evidence for. And then I'm also going to tell you another thing. So here's two kind of bounds on scales. The first one is starting from the axion decay constant f. I claim that for an extra dimensional axion, we have reasonable arguments, or at least a lot of examples and cases where we understand what's going on, where the fundamental quantum gravity cutoff scale, what has also been called the species scale in some of the talks at this workshop, is bounded by 2 pi times square root of s times f, where s is the instanton action, which for a QCD instanton, we just know what it is because we know the QCD coupling. So it's some number of order 100. This is something that I proposed in a paper a couple of years ago. It's something that Tom Rudelius and his student Christopher Tudball, who's here, and I are working on. There was also some other recent work by some folks at Berkeley investigating this. Now I have a second thing I want to propose, not directly related to this, but sort of following, if you believe this, then it's an input to this other thing, which is work that I'm doing with, again, Tom and Christopher, and also Damian Van de Heijstig, who's here, which is that suppose that at some scale there's a supersymmetric 4D EFT description. Okay, that doesn't have to happen. Maybe we start with a fundamentally non-supersymmetric theory in the UV, but suppose that we have 4D supersymmetry at some scale. Then in theories like that are consistent with the world that we live in, we claim that the gravitino mass seems to be bounded by the species scale squared divided by the Planck scale. If you chain these together, measuring an axion and learning about f tells you something about the species scale. Plugging it into this tells you something even stronger about the scale of supersymmetry breaking. So that's interesting. I'm just going to kind of briefly sketch our thinking on this in the last few slides. So experimental discovery of an axion, chaining these things together, tells you the gravitino mass is bounded by roughly f squared over m Planck times some factors in front. And that could rule out a lot of interesting things. It would suggest supersymmetry exists well below the axion scale. If f is relatively small and the species scale is small, it would rule out conventional gut models. Maybe it's also worth noting that in the dark dimension scenario that we've been hearing a lot about the last couple of days, the species scale is something like 10 to the 9 or 10. 10 to the 9 or 10 GeV. So again, it's way below the Planck scale. And in that context, you might expect that the axion decay constant is not so far from that scale, which is also something that Kamran and Naomi wrote a paper about a year or two ago. Okay, so here's some attempts to justify these claims. First, anytime you measure an axion decay constant, you learn something about a cutoff because it's a non-renormalizable interaction. Anytime you see a non-renormalizable interaction in field theory, you know the theory breaks down by some energy scale. That energy scale is like S times F. I'm telling you something a little bit stronger, which is square root of S times F in these extra dimensional models. And the reason it's stronger is that in the extra dimensional model, the axion couples to many more modes. It doesn't just couple to the gluons we know, but it couples to all the Kaluza-Klein excitations of the gluons. And so you have to add up all of those different interactions. And you can plug that into various arguments. I originally made the argument by thinking about sort of a naturalness argument about the propagator of the axion. Benabu, Fraser, Rigg, and Safdie had another version of this where they thought about a scattering experiment. But the point is just sort of any process that involves your axion coupled to your gauge fields and sort of sums over the whole tower of excitations of the gauge fields will give you a stronger bound than if you only think about the zero modes of the gauge fields. And parametrically, this gives you a bound that the UV cutoff of this axion gauge field interaction is smaller than something like F over G. S is 8 pi squared over G squared, so square root of S scales like 1 over G. The exact number you get in front from this kind of argument is not quite as strong as what I was quoting to you, but at least parametrically gives you a similar result. Some other reasoning comes from thinking about the extra dimensional construction themselves. I told you the axion comes from a mode of a higher dimensional gauge field. Specifically, we have some ansatz where higher dimensional gauge field is like axion times some sort of P form that's a function of the extra dimensions. This is a harmonic form. And the thing we do to calculate the axion decay constant is integrate this form, wedge star of this form, over the extra dimensions. Now, in general, this is a complicated geometry problem, especially if you don't have supersymmetry or something to calibrate your answer. But sort of a hand-wavy estimate is that because of the way we've normalized this thing to integrate to 1, we should get something like 1 over the volume of the cycle we integrate over to get the axion, multiplied by the volume of kind of a complementary cycle that intersects it. Yeah, this is fairly hand-wavy, but and there's a coupling constant in front. In the string theory constructions, this is of order the UV scale, like the string scale. This volume that we integrate over to get the axion is proportional to the gauge coupling in the standard model, which also comes from integrating over the same volume. And this other volume is something that you can wrap a brain on to get an axion string in 4D. And so the size of this is related to an axion string tension. And so when this simple estimate works, and it doesn't always, like I said, it was very hand-wavy. It works in a lot of examples. When it works, it tells you there's an axion string whose tension is S times F squared. This axion string tension should be bigger than the species scale because we're sort of starting with some fundamental object and wrapping them on extra dimensions. And if those extra dimensions are not big in fundamental units, then we don't really have any control over what we're doing. So at least if we want to work in a limit where we know what we're doing, this should be true. And if you chain those together, you learn that the species scale is bounded by square root of S times F. This is an instance of something that Tom and Christopher and I have been thinking about that we call electric magnetic co-scaling, which is that it's often the case in theories that the ratio of the mass scale or tension scale of a magnetic object to an electric object is the same as the ratio of their couplings, which by Dirac quantization goes like 1 over the electric couplings. This is very common in examples. It's not universal. There are corners of string theory where it doesn't happen, like near flop transitions where some electric object becomes light, but no corresponding magnetic object does. But then we went and checked the examples where this argument doesn't work. Just examples we can explicitly understand. And we still find that this relationship was true in all of those examples. So, so it seems pretty robust. And this is something we're doing now. So this plot on the left is a plot that came from the Berkeley folks a year ago. They did a scan using a code called CY tools from Demirtas, Rios, Duskon, and McAllister. And basically, I don't know if this is very visible, but there's a dashed line here that they called string tension conjecture. That was the name they gave to the bound that I'm proposing. I don't think it's a very good name for the bound that I'm proposing, but that's what it is. And the black dots are all of the points they checked. And you can see the black dots cluster very close to the line. Tom and Christopher and I are revisiting this. They only worked at certain special points in moduli space. We were worried that maybe things fail near other points in moduli space, especially the ones where this co-scaling relationship doesn't work. And what we have is both some analytic understanding near those limits and numerical scans. Basically, this is some number that should be order 1 or less if the bound is true, and you see it's never much bigger than 1 in our scans. So, so at least within the type 2b landscape, the well-understood part of the type 2b Calabi-Yau landscape, this bound holds really well across examples.
So, like, are there multiple axions that you find from a single?
Axions in most of these. So I don't know if you can see the scale, but this horizontal axis is H11, so it's some Hodge number, and it's order 100 in these examples, and so there are like 100 axions in these different examples, and all of them obey the bound.
I guess related to that, at some point, like you will just assuming order 1 theta angles for each axion, you will start to overclose the universe. Do you know what that number is?
Naomi probably knows.
I was very
So he was asking about like overclosing dark matter in scenarios where you have many axions.
Yeah, it turns out the problem actually gets better when you have many axions because their decay constants come down enough that they can't oscillate enough to.
But they'll be acting as contribution to dark energy. But I guess you're saying there is some other cosmological constant that just fits.
Well, wait, it would only contribute to dark energy if they were lighter than Hubble, right?
Yeah, but I thought that's what you're saying then.
No, I'm saying that their decay constants get small enough that they can't oscillate in their potentials enough to contribute to dark matter.
Okay.
Like you need a large F to get a large contribution to dark matter.
Yeah.
But are they displaced from the middle?
If you assume order 1 displacements from the minimum, then F tells you about what the density is.
You're saying F is like 10 to the A.
Yeah, exactly.
S is supposed to be the action of the leading instant. But
Yeah. Well, this is a little schematic. We actually checked kind of a couple of different variations on how you might try to define exactly what we mean here, and the result seems pretty robust to different choices. But yeah, basically it's you pick some direction in the space to be the axion direction you care about, and you look for kind of the leading instanton that's contributing to that.
What is the y-axis?
Oh, sorry. The y-axis is the largest value in our scan of 2 pi rho squared, where rho is this thing. So basically, that's the thing. Basically, we're conjecturing should not be bigger than 1, or shouldn't be bigger. I mean, the biggest we get is like 6 in examples.
And for S, you're using like the divisor volume.
Right. Well, for C4 axions, yes, we actually checked both C4 and C2. So it's either a divisor volume or a curve volume, depending on the example. Yeah. Okay, so so again, maybe none of these arguments were super airtight, but as an effective field theorist, I find this one sort of reasonably convincing to start with. But then we also have, I think, really good evidence in well-understood corners of string theory that this holds up in general. So if we measure f of an axion and you assume it's an extra dimensional axion, then we learn something fundamental about the scale of quantum gravity, which I think is pretty interesting. I guess I'm already a couple minutes over time. Is it okay if I talk for a couple more minutes? Okay, apologies if I'm going a couple minutes over. I just sort of wanted to briefly mention this other thing, which is something that Damian and Tom and Christopher and I are thinking about, which is that we understand pretty well now infinite distance limits in the string theory landscape. And in infinite distance limits, it tends to be true that the Kähler potential is determined by some logs of some moduli. And so e to the Kähler potential, which shows up in lots of supergravity formulas, goes like 1 over a power of modulus. And when you're going far out in field space, 1 over power of modulus is becoming a small number. It is also true in those limits that the fundamental quantum gravity cutoff scale is usually falling like a power of 1 over modulus. And so they're both falling like powers. The question is just sort of which power is which. But things like the gravitino mass, the formula for that is e to the k over 2 in Planck units times the superpotential in Planck units. And we expect that the superpotential is not very big in Planck units. It might be a little bit big. But this e to the k in infinite distance limits is becoming small, like a power of the species scale divided by the Planck scale. And so what we have been checking is what is the power here? If the power is 1, you would say the gravitino mass is below the species scale, which is not a very interesting thing to say because that's sort of the fundamental cutoff. But if the power is higher than 1, then it becomes interesting. If the power is 2, you say the gravitino mass is less than lambda qg squared over m Planck. So there's the sort of seesaw relationship where it's even smaller. And we find that the power is always bigger than 2, except in examples where the limit you're taking is taking G string to 0. So it's a weakly coupled string limit. In those cases, the power is 1. But at least for any way that I know of embedding standard model phenomenology in those examples, G string going to 0 would send all of the standard model gauge couplings to 0. And the couplings we measure in the real world are order 1 numbers. So there's sort of one uninteresting limit, and we don't seem to be living in it. And then there's all the other limits that are interesting. Since I'm over time, let me not linger on the details. There is a very interesting kind of coincidence between the exponent that appears here and another exponent that appeared in some work on EFT strings by Lanza, Marchesano, Martucci, and Valenzuela that some of you might be familiar with. So I think there's some intriguing story here that we're in the process of unraveling, but I think this bound seems reasonable. Exactly what the order 1 coefficient is, and maybe it's actually like 1,000 and not 1, but this is all work in progress to try to pin down better. But let me wrap up my talk. Axions are interesting for phenomenology. They were invented to solve the strong CP problem. They can also give us natural models of interacting dark matter and dark energy. Extra dimensional axions in particular are good for solving the strong CP problem. I have tried to suggest to you that sort of folklore about quantum gravity not having free parameters might be made more precise in a way that really points to the existence of axions, in particular in standard model-like theories that have light-charged fermions. And I've also suggested that there may be some general bounds that if we can measure an axion decay constant, we learn something about the species scale, and in turn, if there is supersymmetry at any scale, we learn that it must be below an interesting scale. So I think the stakes are very high for axion experiments, not only for the traditional reasons, but because they really might tell us something fundamental about very UV physics. Thank you.